Hello everyone, my name is Abhishek Kulkarni and I'm a PhD student with Professor Jifu at Worcester Polytechnic Institute. Today I'll be presenting our work on synthesis of deceptive cyberdefense with temporal logic constraints. So imagine an attacker who has gained access to corporate network and is now performing lateral movements by exploiting the vulnerabilities in order to compromise some critical assets. In such cases, we need an active defense strategy for the defender to take the necessary actions to prevent the attacker from reaching its goals. In our research, we consider the problem of synthesizing an active defense strategy that is capable of deception and is guaranteed to satisfy a high-level specification of the defender given as a linear temporal logic formula. We choose LTL in our work because it provides us with a very rich language to specify complex temporally extended security objectives, such as always attacker has no root access on the data server, or eventually the attacker must reach to a decoy. However, the traditional approaches of synthesizing strategies with LTL specifications do not consider the case where the defender might be using deception, which is one of the key defense mechanisms in cybersecurity. So let's briefly review how formal methods can be used for cybersecurity. Typically, given in the network, as shown here, we start by abstracting the system as an attacker-defend graph, which essentially captures the dynamics of interaction between the attacker and the defender. In this graph, each state represents a configuration of the network, and the entire state space is partitioned into the attacker and defender states. At each attacker state, the attacker chooses the next move, such as exploiting a vulnerability, and at each defender state, the defender chooses an action, such as network randomization or blacklisting a user, etc. Given such a model, the traditional approach is to use the reactive synthesis, which gives us a quite conservative strategy for the defender satisfying the LTL objective. However, the limitation here is that this approach assumes that both the players have equal amounts of information, which is one of the key reasons behind the conservativeness of this strategy. So imagine the case where the defender is using a decoy-based deception. For instance, at this router, the defender can decide whether the traffic should be sent to host 2 or to the decoy. And this reflects in our attack-defend game graph as seen here. These honeypots here represent the decoys. These states correspond to the configurations where the attacker has reached to the decoy. However, the attacker does not know the locations of these decoys, which leads us to the information structure as seen here. Here, the attacker, as we said, does not know where the decoys are. Thus, in her mind, all of our honeypots would be critical hosts. Whereas the defender exactly knows where he has placed the decoys. In addition, the defender effectively knows the attacker's perceptual game because he is also aware that the attacker lacks the information about the decoys. So this gives us a higher order information structure as shown here, which can effectively be modeled using the Hypergame theory. And given this structure, how do we solve for the strategy of the defender to satisfy the given LTL specifications? To this end, we first observe that the decoy-based deception creates a misperception of labeling function for the attacker. Here, the labeling function essentially assigns to each state which of the propositions hold. In this example, we consider labeling states as goals or decoys. And clearly, because there is a misperception, the attacker would label a decoy state to be a goal state. Given these two perceptual games, in our paper, we propose a single graphical model, which we call as a hypergame and graph, that integrates both these game graphs together and describe an algorithm to compute the deceptive, subjectively rationalizable strategy for the defender. To summarize, the key result that we prove in our paper is that the synthesized deceptive strategy by our algorithm is more powerful than the non-deceptive strategy. As a future work, we are exploring the joint action deception and decoy-based deception, in which we hide the action capabilities also in addition to the placing of decoys. And lastly, we are also exploring the problem of how to place decoys to minimize the probability of attacker reaching to the critical hosts. Thank you.